MDM, mi mail. James Barclay discutirá los problemas de seguridad que trae el uso del Mobile Device Management del Apple Device Enrollment Program, que si bien le permite a los administradores del sistema simplificar muchas de sus tareas, también trae algunas debilidades.
So, hello everyone, my name is James Barclay. I'm a senior R&D engineer at Duo Labs, which is the research arm of Duo Security. And today I'm going to be talking about Apple's device enrollment program. So I'm the only one here today giving this talk, but it goes without saying that this research was truly a team effort. Olabode Anishe, Pepijn Brienne, and Todd Manning all contributed heavily to this research, so I wanted to give them credit up front. So I'm just going to dive into the agenda. Very quickly, I will go over what MDM and DEP are. Then I'll move on to DEP authentication and some of the inherent weaknesses in it. I'll talk about our research methodology, an exploit. Then I'll go into Apple serial numbers and their format. Next, I'll talk about the impact of this research, and then mitigations, and then finally I'll wrap it up with a conclusion. So mobile device management is a technology that's used to centralize the management of end-user computing devices. So these are things like laptops, desktops, mobile phones, and so on. On Apple platforms specifically, it refers to clients, which are Apple devices, and servers that implement support for the MDM protocol. The MDM protocol leverages Apple's push notification service to wake devices and then communicates with the MDM server to receive commands. The client will perform the command and return the output to the server. So what is the device enrollment program? This is a free service provided by Apple to organizations that are using MDM to manage their endpoints. It streamlines the process of MDM enrollment, and it does this by allowing iOS and macOS and tvOS devices that are directly purchased from Apple or an authorized reseller to enroll in MDM during the initial setup. DEP also allows administrators to configure which setup screens are displayed to the end user. So these are things like the Siri setup or Apple ID setup. So throughout this talk, I'll be referring to the DEP API. I wanted to call out that there are 3 different DEP APIs. There's the so-called Cloud Service API. This is used by mobile device management servers to associate DEP profiles with specific devices. Next, we have the Reseller API, which is used by resellers and Apple Retail to enroll devices and check enrollment status and so on. Lastly, we have the Private DEP API. This is an undocumented API that is used by devices to directly communicate with Apple's DEP service. So, unless otherwise noted, throughout this talk, I'm only going to be covering the private, undocumented DEP API that's used by devices to communicate with Apple. So next, I'm going to just go over the enrollment process. So what happens when a device boots up for the first time and checks in with DEP? So there are several asynchronous steps that need to be satisfied in order for a device to enroll in MDM via DEP. Initially, a device record needs to be created by the reseller or by Apple. Then the organization needs to assign the device to an MDM server in the Apple Business Manager portal. Next, the MDM server will retrieve the device record through the Cloud Service API, and then will create the DEP profile. Then the device will authenticate to the DEP API and retrieve what's called an activation record. I'll be talking about activation records quite a bit in this talk. Next, the device will authenticate to the MDM server to retrieve its enrollment profile. So this contains things like the MDM enrollment payload, a certificate payload, and a simple certificate enrollment protocol payload. The device will then request and retrieve a client certificate through SCEP, and then finally, it will authenticate to the MDM server and begin receiving commands. So here's just a more visual representation of that flow. This talk is focusing mostly on step 4, the DEP check-in process. So this is when the device is first involved in communicating with the DEP API. So before I dive in, just wanted to define some of the binaries that we'll be talking about throughout this talk. So first we have the MDM client. I said earlier that when referring to Apple's MDM, it covers clients and servers that implement support for the MDM protocol. The MDM client binary is the client side of that. Profiles is just a utility that's used to manage configuration profiles on macOS. And then Cloud Configuration D, the so-called enrollment, device enrollment daemon, is responsible for communicating with the DEP API. So I said I was going to talk about activation records. To give you an idea of what those look like, we have a screenshot here. This is what is returned by Apple as a JSON blob during the DEP check-in process. Here shown in like a pretty printed format. So you'll notice one of the things here is the so-called configuration URL. This is the URL of the MDM server. That's how the device is going to know which MDM server to communicate with. In addition to that, we've got information about the organization that owns this device. So the organization's email, support phone numbers, physical addresses, and so on. So I'm going to talk a little more about activation records. During this DEP check-in process, the device is going to retrieve this activation record from this URL, iprofiles.apple.com/macprofile. The two functions that are responsible for this are CP fetch activation record and CP get activation record. CP fetch activation record actually retrieves the activation record over the network, and it delegates control to Cloud Configuration D through XPC, which is an inter-process communication protocol defined by Apple. And CP get activation record just retrieves it from the cache. Both of these functions are present in the private configuration profiles framework. So I'm going to talk about how devices are authenticated as part of this DEP check-in process. So the request payload that is sent to this Mac profile endpoint is a JSON dictionary containing two key value pairs. Action, which is the remote action to perform, and SN, which is the serial number. This payload is encrypted using a scheme that's internally referred to as Absinthe. And the serial number in this payload is what determines which activation record is retrieved. So I'll say that again. The serial number in the payload is what determines which activation record is retrieved, not how the device was authenticated. So in this way, DEP effectively only uses the system serial number to authenticate prior to enrollment. So an attacker armed with only a valid DEP registered serial number could potentially enroll a rogue device in an organization's MDM server or just glean information from that activation record. This can be easily verified by changing the VMX file, for example, in VMware Fusion, to be that of a serial number that's registered with DEP. This was originally discovered by Pepijn Brienne, who I did this research with, Victor Vrenchin, and Jesse Peterson. So I'm going to talk about our research methodology. So what were the goals of this research? So once we knew, that only the serial number is required, or is what is used to determine which activation profile or activation record we get back, we set out a way, or wanted a way to automate that. So our goals were to be able to insert any arbitrary serial number during the request for this activation record. Also, we wanted to demonstrate how it's possible to brute force Apple serial numbers, which could be checked against the DEP API in bulk. We also wanted to demonstrate how anyone using these methods can determine which organizations are using DEP and glean information about them, like physical addresses, phone numbers, and so on. And lastly, we wanted to demonstrate that rogue MDM enrollment is possible using these methods. So, as I mentioned previously, changing the serial number in VMware Fusion's VMX file to be that of a DEP registered serial number will, confirm that that is, the only piece of information that determines what activation profile is retrieved. This can easily be verified by using either the MDM client or profiles binary to force a DEP check-in. So on 10.13.3 or older, you would use MDM client, and on 10.13.4 or later, you could use profiles. It's worth noting that the behavior is a little different here, but if you'd prefer to use MDM client, you can simply copy that from a machine running 10.13.3 or older and run it on one of the newer machines. It works just fine. So what MDM client will do when you force a DEP check-in like this is print a pre-printed activation record if the device's serial number is registered in DEP, or an empty activation record if not. With profiles, if you enable MDM debug logging, it'll write the activation record to this log file at manageclient.log. Additionally, you'll see this pop up on your Mac that says this device can automatically configure your Mac if it hasn't previously completed. So, like I mentioned earlier, once we knew that only the serial number was, or the serial number is all that's required to authenticate to this DEP API, we set out to automate this process and demonstrate how an attacker might, use this to retrieve activation records in bulk. So we considered three approaches. We could reverse engineer the protocol between Cloud Configuration D and the DEP API, which is internally referred to as Tesla, and the encryption scheme, which is internally referred to as Absinthe. We also considered, if it was possible to man-in-the-middle requests to iprofiles.apple.com/macprofile, and then finally instrument the binaries that directly interact with this API. So reverse engineering this Tesla protocol. The Cloud Configuration D binary will request this activation record, which I mentioned previously contains these two key value pairs, the action and serial number. The payload in this request is encrypted using a scheme internally referred to as Absinthe, and is then base 64 encoded and used as the request body in an HTTP post to that endpoint. In Cloud Configuration D, fetching this activation record is handled by the MC Tesla configuration fetcher class. So the general flow of MC Tesla configuration fetcher enter state is listed here. We explored each of these methods somewhat deeply, but ultimately it just led us further down the rabbit hole, and we decided to explore other methods of being able to modify the serial number that is presented to the DEP API. So the next approach that we considered was man-in-the-middling requests to the DEP API. Cloud Configuration D does certificate pinning, but we found that this can pretty easily be changed by flipping the MC Cloud config accept any HTTPS certificate flag to true. But like I mentioned earlier, this payload is encrypted, so it wasn't feasible to modify it before it's actually sent to the API without having the keys required to decrypt it. So lastly, we looked into instrumenting the system binaries that directly interact with the DEP API. This has the benefit of being able to leverage the existing flow or infrastructure, and with just adding our own little bit of functionality right before the payload is signed. It's worth noting that for this to work, because Cloud Configuration D is a protected binary under System Integrity Protection, or SIP, that it needs to be disabled. We recommend doing this on a non-critical virtual machine because SIP is actually a pretty useful security feature. So with SIP disabled, we can attach to Cloud Configuration D with LLDB. You'll notice that we need to use sudo because Cloud Configuration D requires elevated privileges. Then we can just wait for the Cloud Configuration D process to attach. So while we're waiting, we can force the DEP check-in in order to force Cloud Configuration D to attach and then begin our debugging session. So one of the first things we wanted to do once we have this debugging infrastructure set up is look into how we could just modify the serial number that's returned from the I/O registry. This is done in Cloud Configuration D, and as far as we know, that's the serial number that's sent to the DEP API. So we thought if we could modify that, then it would change what is sent to in that payload. So we were able to modify the serial number retrieved from the I/O registry by initially setting a breakpoint for I/O service get matching service. We then created a new string variable containing an arbitrary serial number and then just modified the register to point to that variable we created. So this can be seen in this listing here. We set a breakpoint for I/O service get matching service, wait for the Cloud Configuration D process to attach, continue, and then just step through the execution of the program until we can see that the R14 register contains our serial number. Then we just create a new serial number and then write the register to point to that new variable. But unfortunately, for whatever reason, this didn't actually modify the payload that is sent to that Mac profile endpoint. But something did. So I'll talk about what actually worked. So once that initial process failed, we looked to find the closest point where the serial number is still in plain text before it gets signed. It appeared that the best place to look was this MC Tesla configuration fetcher start configuration fetch method, which does the following. It creates a new NS mutable data object, calls this set configuration data method, passing it the new NS mutable data object, calls this profile request dictionary, which returns that dictionary that contains those two keys that we've seen earlier. It then serializes this dictionary to JSON, signs the JSON payload, base64 encodes it, and then does a bunch of other stuff, like sets the HTTP header to post, sets the body to the base64 encoded payload, sets some HTTP headers like X profile protocol version is set to 1, and the user agent is set to config client 1.0. Finally, it's going to use NSURL connection to perform the HTTP request. So understanding this flow of the MC Tesla configuration fetcher start configuration fetch, this allowed us to modify the dictionary containing that profile request before it's ultimately converted to JSON. So to do this, we set a breakpoint for data with JSON object. So as you'll see in this listing, we set the breakpoint for the regex data with JSON object, wait for Cloud Configuration D to attach, continue the execution, and then we create a new NS dictionary object in memory containing both the it's that payload that gets sent to the Mac profile endpoint. So an arbitrary serial number, and then we just update the register to point to that NS dictionary. And that worked. So with just a few LLDB commands, we were able to insert an arbitrary serial number and get that serial number's activation record back, not the serial number of the Mac we were using. So as you can see here, we have someone else's activation record. So one more thing though, I think Steve Jobs said it best: LLDB, Python, interface. These are not three separate things. No, not really. But once we had the initial proof of concept, we wanted to show how we could automate this. Fortunately, the LLDB API is available in Python through this script bridging interface. which is installed by default if you have the Xcode developer tools installed. So that made it relatively easy to just write a script that takes a list of serial numbers and then injects them into Cloud Configuration D to check for the DEP profile or activation record. So next I'm going to talk about Apple serial numbers because we think it's important to understand how easily these can be brute forced. This is an example of an Apple serial number. It's just a string of letters and numbers. But through this research, we were able to demonstrate that how easily Apple device serial numbers can be brute forced. So there's actually enough information in the serial number to limit the search space pretty significantly, which would increase the speed with which an attacker could generate serial numbers and then check the DEP API for the activation records in bulk. So what would this allow an attacker to do? So if they're able to brute force these serial numbers and leveraging this exploit, it's feasible that an attacker could determine exactly which Apple customers are using the device enrollment program, build a data set mapping the serial number to the organization that owns the device, or build a data set mapping the serial number to the complete activation record. We think it's feasible that an attacker could use this information to further target organizations. So I'm going to talk a little bit about the serial number format that Apple uses. Apple serial numbers use a 12-character format that have the following 5 components. It's worth noting that 11-character serial numbers also exist, but these are used on older Apple devices. So with the 12-character serial numbers, we have a plant code, the year it was manufactured, the week it was manufactured, a unique unit code, and then the device model identifier. So the plant code is the first part. It's 3 bytes at position 0. The only known plant code on Mac devices is C02, but we don't know how many plant codes exist for other devices. On iOS devices, for example, there are many plant codes. The year of manufacture is 1 byte at position 3. And uses the range listed below. Vowels and the character B are removed from that range. Additionally, each year has 2 possible characters associated with it that correspond to the early or late moniker sometimes used in Apple product names. So the epoch associated with this numbering scheme starts with C, which represents early 2010, all the way up to Z representing late 2019. So we don't yet know what will happen in 2020, if Apple will roll that over or just stop making computers and iPhones. We'll see. Next, we have the week of manufacture. This is denoted per half year. If the code is in the second half of the year, it indicates an offset from the 27th week of the year, and it uses a single byte in the following range. Similar to the year of manufacture, the week of manufacture removes or omits the characters B, S, Y, and Z. It's not documented why, but it makes sense or stands to reason that this is because they're visually similar to other characters. Next, we have the unit code. This is 3 bytes at position 5, and it's unique to each device within its model, year, week of manufacture, and plant code. So this is the biggest source of entropy in Apple serial numbers. It's a base 36 scheme, and it uses the range listed below. So there are 6,656 possible values within that range that I mentioned earlier. Next, we have the device model identifier, which is a 4-byte ID that is created from a finite set of codes that Apple maintains for their hardware models. The most comprehensive source of these IDs that we've found is on Piker Alpha's GitHub repository. He has those all listed there, or most of them, not all of them. So knowing that, we can break apart the serial number I showed earlier. We have the plant code. We can see that it was manufactured during the second half of 2016, the 48th week of 2016, we see this unique unit code, and then the model associated with that ID, which is for the MacBook Pro 13-inch 2016 4 Thunderbolt 3 ports. And yes, that's the real product name. So next I'm going to talk about the impact of some of this research. So we basically see two scenarios where, where this could be leveraged by an attacker to expose sensitive information about an organization. Initially, just obtaining the DEP activation record couldn't allow an attacker to just build up a data set or just expose information about the organization that owns a particular device. Next, it's feasible, depending on the configuration of the MDM server, that an attacker could perform a rogue MDM enrollment. So basically, like stealing the identity of a corporate device. So the information disclosure issue is, we see that it's possible that an attacker could use this, the information retrieved from the DEP activation record in combination with the serial number to aid in social engineering attacks, such as like calling the help desk and asking for password resets, or help installing some software, or who knows. Next, the rogue DEP and MDM enrollment. So the MDM protocol provided by Apple supports, but it doesn't require authentication as part of the enrollment process. So that means without any additional protections, all that would be required to enroll a device in a company's MDM server would be this, the serial number of the device. Once enrolled, a lot of things could be deployed by the MDM server. The configuration profiles, which are delivered via the MDM protocol, contain support for delivering VPN configuration data, Wi-Fi passwords, certificates, private keys, you name it. So next I'm going to talk about mitigation. So we think there are a couple of things that Apple could do to mitigate this issue. One thing that we think would be possible is leveraging the unique ID that is generated in the secure enclave on the T1 and T2 chips. This is also present on iOS devices. It's worth noting, though, that this may not be feasible until every Mac device contains one of these coprocessors. Additionally, we found no evidence of strict rate limiting on this Mac profile endpoint. This could be because it might be difficult for Apple to distinguish between, let's say, an attacker hammering the DEP API or an organization that just bought 1,000 Macs and is enrolling them all at once behind the same NAT router. Additionally, we found that although this endpoint is called Mac profile, it will happily accept iOS serial numbers and retrieve the activation record of iOS devices that you submit to it. Lastly, we think requiring strong authentication prior to the DEP enrollment happening would mitigate this as well. So there are also things that customers can do that are leveraging DEP and MDM, regardless of some of these risks outlined in this talk. So, like I said earlier, the MDM protocol supports user authentication, so if possible, turn that on. In addition, we think that just because a device is enrolled in MDM shouldn't afford it any additional privilege within your network. So require strong user authentication post-deployment before sending down like any sensitive information. And also, Apple documents these best practices in the Apple Business Manager help documentation. So moving on to the conclusion. So it's also worth noting that DEP still provides value. We're not telling people that you shouldn't use DEP or MDM because we think that the benefit of having securely managed devices outweighs some of the inherent risks in how DEP authentication works. Also, Apple could be doing more to strongly authenticate devices, but it might take time for this to become fully realized. For example, like with device attestation, that might require new hardware. Next, don't treat devices as trusted just because they're enrolled in MDM. Require strong authentication post MDM enrollment before sending sensitive configuration data. And then lastly, if possible, enable user authentication as part of your MDM enrollment process. So this is the disclosure timeline, starting with when we initially discovered this authentication weakness and reported it to Apple, leading up to the research being published. I also want to thank Jesse Endahl, Max Bellinger, Victor Vranchin, Jesse Peterson for their contributions to the Mac security community, and specifically their DEP and MDM research, as well as Piker Alpha for documenting so much about the Apple serial number format. And that's it.